This video is about enzymes. Now, there's a lot of information in here, so I want to make sure that you remember to use the techniques of pausing the video and rewinding it in order to get all of the information that I'll be covering. So I'll be trying to go, not really quickly, but I'm trying to keep these to about like 8 or 9 minutes, and in order to do that, we're going to have to move through this kind of quickly. But to start off, I'll just talk about some basic information about enzymes. Enzymes are made of proteins. So we'll talk about the 4 major macromolecules as our next topic. Proteins are one of these, and you should be aware of that to begin with. That's what enzymes are constructed out of. By the way, please note we're using the red lightsaber because this is getting into some heavy chemistry, and that is truly evil. So we've got the red lightsaber here to represent that. The other term you should be aware of is referred to as the substrate. The substrate is the material that the enzyme is acting upon. Now, there are a few different things that enzymes can do to the substrate. We'll get into that as the video progresses a little bit. But to start off, I want to show you a simplified version of how an enzyme works and relate it to something that all of you have experienced. They refer to enzymes as using what's called a lock and key mechanism. So if we think of the key as the substrate, remember the substrate is the material the enzyme is acting upon, the lock is the enzyme itself. The way it works, if you have the appropriate key and lock, is that the key not only will fit in there, but it will turn and open the lock. So each enzyme is unique, just like each lock and key combination is unique. This means your body has to make specific enzymes in order for it to be able to react with a certain substrate. Now, taking this out of the example and looking more into a scientific version of it, the enzyme has a particular shape, much like the lock has a particular shape and like the little tumblers inside the lock. The substrate has a complementary shape that then fits in there. Usually once it binds to the enzyme, this is called the enzyme-substrate complex, so the two of them together. Usually the shape of the substrate will change. Sometimes it's just molded differently, sometimes it's combined with something else, other times it's broken apart. We'll get into some of that stuff as the video progresses, but what you should understand from this is that the substrate has to have the appropriate shape to fit in the enzyme. Enzymes only work for one particular substance. An example of something like this is if you know someone who's lactose intolerant. This person, when they ingest lactose, which is the sugar found in dairy products, they don't have the appropriate enzyme to break that one down. Now, being lactose intolerant is kind of a mild problem in modern time because you can take lactase, which is like a pill form of the enzyme that breaks down the lactose in milk. So as long as you're taking those pills, then your body has the ability to break that stuff down and process it. But someone who's naturally lactose intolerant is not producing the correct enzyme in order to break down that sugar in milk. To talk about our next topic, we're actually looking at the speed of reactions. Now, in general, what enzymes end up doing is they speed up a reaction. Now, we'll actually have Mr. Snelling here to help us with this, because I think otherwise graphs and things tend to get a little bit boring. So Mr. Snelling is gonna help us point out some of this chemistry witchcraft that we're talking about as far as enzymes go. What you need to understand first, I guess, whenever we're looking at a graph, we'll get Mr. Snelling out of our way for a second, is what's located on our x and y axes. So on the x-axis here, we have the substrate concentration. So basically the amount of the substrate, and then this is the reaction rate, so how quickly the reaction is happening. Because what enzymes do, they actually help speed up reactions. So if there's no enzyme, the reaction progresses at a steady rate. I guess we should use Mr. Snelling to help us point this out. So you can see here, as Mr. Snelling points, the enzyme, or the no enzyme reaction, happens at a steady rate for us. The reaction with enzymes happens at a much faster rate. You can see this is what's called exponential increase in the beginning, where it's increasing very, very quickly, and then it does eventually level off. So like the speed of the enzyme, the help from the enzyme eventually levels out. So if you have like a certain amount of enzyme, it's only going to help to a certain extent. But it does help to speed up reactions that are taking place inside the body. Now, as Mr. Snelling will point out for us in a second, there are some things that impact how fast these enzymes can work. That's part of why things started to level off in the previous example. One of the things that can impact enzyme function, as Mr. Snelling helps us point this out down here at the bottom, is temperature. There is an optimum temperature for each enzyme. For this particular example, the optimum temperature is around 40 degrees Celsius. Once we increase to about maybe 63 degrees Celsius, the enzyme stops working completely. Now, it does work well all the way down to a freezing temperature of 0, but you can see that the enzyme function drops off dramatically. So for all enzymes, there's going to be an optimum temperature where that enzyme works the best. So you can see for this one, again, it's right around 40 degrees. What ends up happening to the enzyme if you get beyond that is it denatures. It basically loses its shape and it stops working. So that's why we see it totally drop off here. The enzyme shape, that matched up with our key, with our substrate, that is going to change if the temperature gets too high. Our final one to look at, and you'll do some activities in class that tie this together, is pH. So there is also an optimum pH, just like there was an optimum temperature. For this particular example, our optimum pH is 8, so a weak base. What you see here again is at around 10.5, the enzyme function drops off to nothing, meaning that at this point the enzyme decharacterizes, its shape changes, and that key, the substrate, no longer fits in it. Same thing happens once it becomes too acidic, so a little bit down below 5, it starts to break down and the enzyme doesn't function there either. So all enzymes will have an optimum pH and an optimum temperature at which they will function. Like I said before, you'll do an activity that's going to really help point this out to us as we work our way through the chapter. On to our final topic. The last thing to talk about are the two different types of enzymatic reactions. The first one is referred to as a catabolic reaction. This is going to break things down. An example of a catabolic reaction would be this one here. So we have our enzyme. Our enzyme is accepting maltose. You can see the shape that it has. Maltose will fit in what's referred to as the active site of the enzyme. This is where the reaction is taking place. So maltose has the correct shape. It fits in there. What the active site of this enzyme does is it breaks the bond between the two sections of maltose, and we end up breaking that one down into two glucose molecules. Now we'll talk about glucose and maltose once we begin discussing the different biomolecules at the end of the chapter. Glucose is what's called a monosaccharide. Maltose is a disaccharide because there are two of them bonded together. This, though, is considered a catabolic reaction because it is breaking things down. This is also what happens in your digestive tract. I mentioned lactose and lactase to you earlier. Lactose, remember, is the sugar in milk. Lactase is the enzyme that breaks that down. That is also a catabolic reaction because it's breaking something apart. Now, as you can probably imagine, if a catabolic reaction is something that breaks something down, an anabolic reaction is going to build something. Think about anabolic steroids, right? It helps you build muscle and get bigger. In this case, an anabolic reaction is just going to be putting two pieces of substrate together. So again, if we look at our shape, our active site has this pretty much a key shape that fits this piece, and then a triangular shape that fits this next piece. One thing to point out, they're not actually shaped like this, but this is just a good example of showing you that it is a unique formation that's going to fit a particular substrate that will then join up appropriately with that enzyme. You can see those two fit into place perfectly, and then what ends up happening with our enzyme is it bonds those two things together to make a product at the end. So in this case, our anabolic reaction is building something. It's taking two smaller pieces and putting them together to make a single product at the end, whereas our catabolic process was the exact opposite. It took something that was already built and breaks it apart into something more simplistic. Both types of enzymes are extremely important. Catabolic enzymes mostly function as part of your digestive process. Anabolic processes then take the things that your digestive process broke down and it builds the materials that your body needs. So as always, make sure you take some time after this video to answer the questions, and I'll see all of you in class. Thank you.